Welcome to the Learning Assistant app YouTube channel. Imagine you are in a laboratory in the early 1800s. You're measuring the weights of solids and liquids, and the numbers are messy, full of complicated decimals and uneven fractions. But then you turn your attention to gases, and suddenly, the universe starts behaving with a strange mathematical elegance. Why is it that when gases react, they do so in perfectly neat, simple ratios? This was the observation made by Joseph Louis Gay Lussac in 1808, and it remains one of the most beautiful insights in chemistry. Let's visualize what he saw. Imagine we have a container of hydrogen gas and a container of chlorine gas. If we let them react to form hydrogen chloride, we notice something striking. 1 liter of hydrogen combines with exactly 1 liter of chlorine to produce exactly 2 liters of hydrogen chloride. Notice the ratio, 1 to 1 to 2. No messy remainders, no half-liters left over. It's a clean, whole number relationship. But let's look at a slightly more complex example to see if this pattern holds. Picture 2 liters of hydrogen gas. Now, let's bring in 1 liter of oxygen. When they react to form water vapor, you might expect 3 liters of product. But watch what happens. We get exactly 2 liters of water vapor. The ratio is 2 to 1 to 2. Again, we see these simple, small integers. This is the heart of Gay-Lussac's law, when gases react together to form other gases, and all volumes are measured at the same temperature and pressure. The ratios of those volumes can be expressed as simple, whole numbers. But wait, why does this happen? Why doesn't nature give us a ratio like 1.43 to 2.7? The aha moment comes when we realize that volume is a macroscopic proxy for something microscopic. A few years after Gay-Lussac's discovery, Amedeo Avogadro provided the missing link. He suggested that equal volumes of gases contain the same number of molecules. Think about what that means for our hydrogen and oxygen example. If the volume ratio is 2 to 1, it's because we literally have twice as many hydrogen molecules as oxygen molecules. The simple volume ratio we see with our eyes is just a giant scaled-up reflection of the individual molecules reacting one by one. As you can see, Gay-Lussac's law is more than just a rule for lab technicians. It's a window into the discrete, atomic nature of our world. It tells us that even in the invisible, chaotic clouds of a gas, there is a fundamental order. The next time you look at a chemical equation involving gases, remember that those coefficients aren't just abstract numbers on a page. They are a direct map of the space those gases occupy. Nature, it seems, prefers to keep its recipes simple. Thanks for watching, and keep exploring the hidden patterns of the universe with the Learning Assistant app.